Have you ever wondered how a machine weighing 50 tons, vibrating, moving over rough terrain at 40 kilometers per hour, operating in conditions of dust, rain, darkness, and extreme stress, is capable of putting a projectile through a window 3 kilometers away? It is not luck. It is not simply brute firepower. It is an accumulation of decades of applied physics, precision electronics, and materials engineering working together in perfect synchrony during the brief instant the cannon fires. And every one of those systems has to work correctly at the same time, because in armored combat, a half-meter error at 3 kilometers is not a technical failure. It is the difference between destroying the target and being destroyed yourself. The first problem a modern tank has to solve is one that seems basic but conceals formidable complexity: knowing exactly where the target is. Not approximately. Not with a 10-meter margin of error. With enough precision that a projectile which will take more than a second to travel the distance between the cannon and the target arrives at the exact point where the target will be when the projectile gets there, not where it was at the moment of firing. This requires simultaneously solving several overlapping physics problems that change in real time. The laser rangefinder is the starting point. When the gunner identifies a target, the system emits a laser pulse that travels to the target and returns. By measuring the exact time that pulse takes to make the round trip, the system calculates the distance with a precision that can be within 5 meters at ranges of 3 or 4 kilometers. It seems sufficient, but in reality it is only the first piece of data in an equation with many more variables. The distance to the target is only the starting point. What the fire control system needs to calculate is the complete ballistic trajectory of the projectile, and that trajectory is determined by a number of factors that most people would never consider. The initial velocity of the projectile as it leaves the cannon varies according to the temperature of the propellant. A round of ammunition that has been stored in a tank under the desert sun for hours has a different internal temperature than one stored in a tank operating in the Arctic. The chemical reaction of the propellant is sensitive to temperature, and that sensitivity translates directly into variations in the initial velocity of the projectile that can mean several meters of error at the point of impact at long range. This is why modern tanks have sensors that measure propellant temperature and correct the ballistic calculation accordingly. The temperature of the cannon itself also matters. After several consecutive shots, the metal of the barrel expands from the heat. That expansion changes the internal dimensions of the tube and affects the exit velocity of the projectile. Furthermore, a hot barrel can experience thermal droop, a microscopic curvature caused by uneven heating of the metal, which deflects the line of fire even though the aiming system indicates the cannon is pointing correctly. The most advanced tanks have thermal sensors distributed along the barrel that measure this temperature gradient and calculate the resulting deviation to correct it before firing. Crosswind is another factor that seems minor, but at 3 kilometers can deflect a projectile several meters from its calculated trajectory. Modern tanks have anemometers that measure wind speed and direction in real time. But the wind the sensor measures at the tank's position is not necessarily the same wind the projectile will encounter along its entire trajectory. The fire control system uses atmospheric models that estimate the wind profile at different altitudes along the projectile's path, integrating that information into the lateral correction calculation. The curvature of the Earth also enters the equation when firing ranges are long enough. A projectile traveling 3 kilometers along the Earth's surface is following a trajectory over a surface that curves slightly away from it. At ranges of 2 or 3 kilometers, the effect is small, but not negligible when maximum precision is sought. Modern fire control systems incorporate a correction for Earth's curvature and also for Earth's rotation, the Coriolis effect, which deflects long-range projectiles to the right in the northern hemisphere and to the left in the southern hemisphere. But none of these calculations are worth anything if the cannon is not pointing exactly where the fire control system has calculated it should point. And this is where one of the most sophisticated systems in the entire tank comes in: the turret stabilizer. A moving tank is a platform that vibrates, oscillates, and bounces over terrain. Without stabilization, the cannon would follow all those movements and it would be impossible to maintain aim on a target while the vehicle is moving. Modern 2-axis stabilizers use gyroscopes and hydraulic or electric actuators that detect every movement of the turret and cannon and compensate for them in real time, keeping the cannon aimed at the target regardless of what the tank's hull is doing underneath. The precision of these systems is such that a modern tank can fire with a high probability of a first-round hit while moving at field speed over rough terrain, something that would have seemed impossible 50 years ago. The projectile itself is a marvel of engineering compressed into an object less than a meter in length. The most common projectiles used against heavy armor are kinetic energy penetrators, known as APFSDS rounds. They are not explosive. Their destruction mechanism is not chemical but purely kinetic. They are long, thin rods made of tungsten alloys or depleted uranium, materials chosen for their extraordinarily high density, which exceeds that of any conventional steel. These rods are accelerated by the propellant to velocities that can exceed 1,700 meters per second, almost 5 times the speed of sound, and when they impact the armor of an enemy tank, the kinetic energy concentrated in a tip of reduced diameter generates pressures so extreme that the armor steel behaves like a fluid and the rod passes through it. There is no explosion. There is no controlled fragmentation. Only pure kinetic energy converting solid steel into plasma in microseconds. The other main type of ammunition is the shaped charge projectile, designed to penetrate armor through the Monroe effect, also known as the Monroe effect or the hollow charge effect. These projectiles contain a metal cone, usually copper, surrounded by a high-performance explosive. When the projectile detonates at the correct distance from the target armor, the explosion collapses the copper cone inward at velocities exceeding 10 kilometers per second, forming a hypersonic jet of metal that penetrates the armor through the extreme concentration of pressure in a minimal area. The armor does not break, it is pierced, as if a needle of liquid metal passed through it in microseconds. The metal fragments that enter the interior of the attacked vehicle are what cause the real damage to systems and crew. The tank's vision system is the link that connects all this firepower to the real world. Modern tanks have thermal sights that detect the infrared radiation emitted by objects, allowing the gunner to see targets in complete darkness, through smoke, fog, or dust raised by combat. An enemy tank engine that has run recently emits a thermal signature clearly distinguishable from the environment, even when the vehicle is visually camouflaged. The most advanced systems combine thermal vision with visible light image amplification and can present the gunner with a fused image that combines the best of both sources. Additionally, modern systems include automatic target tracking capabilities. Once the gunner identifies and designates a target, the system tracks it automatically even if the target maneuvers or the tank moves, keeping the fire solution updated in real time. The pace of this entire process, from the moment the gunner identifies a target to the moment the projectile impacts, can be just a few seconds in a well-trained modern tank. The fire control system measures the distance with a laser, reads the wind sensors, propellant temperature, barrel temperature, and terrain inclination, calculates the complete ballistic correction, elevates the cannon to the exact angle needed to compensate for the parabolic trajectory of the projectile, applies the lateral correction for wind and target movement, and the gunner pulls the trigger. From the shot to impact at 3 kilometers, less than 2 seconds pass. In those 2 seconds, the projectile has traveled at speeds exceeding 5 times the speed of sound, has followed a trajectory calculated by a ballistic computer that has processed dozens of variables simultaneously, and has arrived at a point in space with precision that in many cases is within 30 centimeters. What you see when a war tank fires is not simply a destruction machine unloading brute force on the world. It is a measurement, calculation, and control system that has more in common with a precision scientific instrument than with a weapon in the conventional sense of the word. Every sensor, every algorithm, every material in the projectile and the cannon exists because someone solved a physics problem that would otherwise have made impossible what seems so simple from the outside. Aim, fire, hit. And to do it again and again, while moving, at night, under enemy fire, with a reliability that civil engineering would envy. The next time you see images of a tank firing on a news broadcast, what you are seeing is not raw firepower. You are seeing decades of applied physics compressed into an instant of less than 2 seconds. And almost none of the most important parts of that process are visible to the naked eye. Yet there is an additional layer of complexity that most analyses of tank precision never get around to mentioning, because it occurs at a level that not even the gunner consciously perceives. It is the layer of complete system integration, the moment when all the subsystems described so far cease to be individual components and become a single organism that makes decisions faster than any human being could process. The fire control computer of a modern tank is not simply a sophisticated ballistic calculator. It is a data fusion system that is receiving information from between 15 and 20 different sensors simultaneously and continuously, even when the tank is not firing. The inclination of the hull on 2 axes, measured by accelerometers. The speed and direction of vehicle movement, calculated from encoders on the drive wheels and corrected by the inertial navigation system. The external ambient temperature. Barometric pressure, which affects air density and therefore the aerodynamic drag the projectile will encounter along its trajectory. Relative humidity, which also influences air density in a way that is not negligible at long ranges. The rotation speed of the cannon during the stabilization process. And dozens of internal system parameters that the gunner never sees on the screen but that the computer is monitoring and weighting constantly. What the computer does with all this information is execute in real time what engineers call a complete ballistic solution, a mathematical model that simulates the complete trajectory of the projectile from the moment it leaves the cannon to the moment it reaches the target, accounting for all the forces that will act on it during that journey. It is not a simple calculation. The trajectory of a projectile is not a perfect parabola, which would be the case in a vacuum under constant gravity. It is a complex three-dimensional curve determined by gravity, which varies slightly with latitude and altitude, aerodynamic drag, which depends on the projectile's speed and changes as it decelerates, the Magnus effect, the deviation caused by the rotation of the projectile on its own longitudinal axis produced by the rifling of the barrel, crosswind deflection, which varies along the trajectory, and the correction for the movement of the tank itself at the moment of firing, which introduces a lateral velocity component to the projectile. The Magnus effect deserves particular explanation because it is one of the least intuitive factors in exterior ballistics. When the projectile leaves the cannon, the helical grooves cut into the interior of the barrel impart a rotation on its axis that can exceed 300,000 revolutions per minute. This rotation is essential for the gyroscopic stability of the projectile in flight, the same reason why an American football thrown with a spiral flies straight while one thrown without rotation tumbles and veers off course. But the rotation also generates a lateral force perpendicular to both the direction of flight and the axis of rotation, exactly like the force that curves the trajectory of a tennis ball hit with topspin. This force, the Magnus effect, deflects the projectile from its flat trajectory in a predictable but calculable way that must be compensated for. In a shot at 3 kilometers, the deflection from the Magnus effect can be several decimeters, enough to turn a direct hit into a miss. The ballistic computer calculates it based on the rotation speed of the projectile, its geometry, and air density, and incorporates it as a lateral correction in the aiming angle. But the physics of the shot is only part of the story. There is a dimension of armored combat that no sensor can measure directly and that no algorithm can calculate with certainty: the behavior of the target. If the target is a moving vehicle, the fire control system has to predict where that vehicle will be when the projectile arrives at its position, not where it is now. This requires estimating the current speed of the target, its direction of movement, and assuming that speed and direction will not change during the projectile's flight time. This estimate is called the lead angle, and calculating it correctly is one of the most complex challenges in fire control in real combat. Modern automatic target tracking systems solve this problem by measuring the change in the target's position between two successive instants, calculating its vector velocity, and projecting that velocity forward by the projectile's flight time. But this only works if the target maintains constant speed and direction. An enemy tank driver who suspects he is being aimed at and executes unpredictable evasive maneuvers can frustrate this calculation. The most advanced tanks have systems that analyze the target's movement pattern for several seconds before firing, attempting to identify whether the movement is rectilinear, curved, or erratic, and adjust the position prediction accordingly. It is not perfect. War never is. But statistically, it significantly increases the probability of a first-round hit, which in modern armored combat is the only shot that may matter. The armor of the firing tank also deserves attention, because the precision of the shot is worth nothing if the tank is destroyed before it can fire. Modern composite armor, the best-known example of which is Chobham armor originally developed in the United Kingdom, is not simply a thicker steel wall. It is a multi-layer sandwich of materials with complementary physical properties. Layers of high-hardness steel, ceramic layers, fiber composite material layers, and in some configurations, spaced steel layers with air chambers between them. Each material is chosen to degrade a different penetration mechanism. Ceramic is extraordinarily hard and compression-resistant, which causes the kinetic penetrator to fragment or deflect when attempting to pass through it. High-hardness steel absorbs and disperses impact energy. The spacing between layers causes shaped charge projectiles to detonate at suboptimal distances, reducing the effectiveness of the hypersonic metal jet. Above this passive armor, the most modern tanks incorporate active protection systems that represent perhaps the most radical technological leap in the history of armor. An active protection system is essentially a miniaturized point defense system mounted on the tank. Short-range radars distributed around the vehicle detect incoming projectiles or missiles, calculate their interception trajectory, and when impact is imminent, fire a fragmentation charge that destroys or deflects the enemy projectile before it reaches the armor. The Israeli trophy system, one of the most advanced in service, can intercept rocket-propelled projectiles and guided anti-tank missiles within less than a meter of the vehicle, and can do so multiple times in rapid succession against multiple simultaneous threats. It is a system that operates completely outside the bounds of human reaction capability. From detection of the incoming projectile to interception, between 0.3 and 0.5 seconds pass,